Okay. So a couple of things. I have been on stage speaking since I was literally 9 years old. Gratitude to mom and dad. They were the ones who said, she's adorable when she does this, so we're just going to keep sending her to these conferences until it turns into a job. One thing you learn is to adapt on the fly. I will not keep you over time unless you really want to stay over time, and then we can talk about fairness all day long. My name is Melinda Thielbar. I'm a vice president of data science at Fidelity Investments. This is actually a talk from Melinda Thielbar, private citizen, about an open source software called Jurity. Jurity is sponsored by Fidelity Investments, so the software has our brand on it. However, I have been told multiple times, whatever you say is on your own head, so I am not speaking for Fidelity today. Brief primer. Has anybody done fairness testing for your models? Okay, a few. Very, very small number. So here's the good news. It is easier than you think. So the way fairness testing works is that if you group everybody up and you look at your model performance metrics, that can hide problems for people that you don't have a lot of. So for example, if you were hiring for tech in the mid-90s, you didn't have many resumes from women. And so when you actually did your fairness metrics on any of your hiring models, there were problems for people who were women, people who identified as black, whatever. You didn't see them. And so somebody sensibly said, well, I tell you what, and in this case, this is represented by the green circles and the blue squares. And somebody sensibly said, well, I tell you what, just group everybody up who we think is in a disadvantaged demographic and make sure that your model metrics, whatever they are, false positive, false negative, false discovery rate, whatever you're looking for, make sure that theirs matches everybody else's and go on with your life, right? And we got very far with that. And the pushback on just doing that was crazy for a while. It was like, well, maybe girls are just bad at math. And I'm like, maybe you're just a bad person. Oh, should I have said that? I'm sorry, right? But then we figured out that it's not that girls are bad at math, probably. We can talk about that in detail. If you actually go down the causal model for fairness, right? If you look at the causal rubric for observed data, and you kind of check all the boxes for historically disadvantaged people, it's a really strong argument that it's not that women are bad at math. For example, I'm allowed to say that. It's a really strong argument for true bias. So there we are. We said, okay, the model, we don't want to build AI models that like push this bias, right? We don't want to build AI models that take a hiring manager's biases and scales them out to the rest of the world. That's crazy. We want to catch that before it goes out into the open, and that's what fairness testing is for. It's to keep from accidentally, inadvertently, taking biases in your process and scaling them out into the world so that now it's not just this one hiring manager somehow has a team that all looks like that person. If you build a model on that, now it's everybody at the company looks like that, and that's a mistake. We don't want that to happen. All right. So this was great. We said, all right, we developed all these methods, and we talked about the statistics, and we talked about what cutoffs make sense. And then as I started getting into fairness testing, one of the things I noticed was that in a lot of cases, you did not have the demographics you wanted, right? So you want to make sure that this model's not biased against people of color. It's not biased against people by gender. In a lot of cases, where there are laws, we actually collect that data, and we actually ask you to please self-identify so we can make sure our hiring practices, our credit granting practices are not unfair. But in a lot of other instances where we use AI, we don't collect that information. We don't have a way to secure it properly. And when I say we, I mean we as a society. And people are really unwilling to share that data, right? You really want to fill out a full demographic profile on yourself for every company that uses AI. A lot of people are really skeptical of that. They're really skeptical that the company will protect that information, and they're really skeptical that the company will only use that data in the way that they say they will use it. And even if we were to magically wave a wand right now and start collecting demographics for everybody, and everybody freely, openly shared that information, we took care of it perfectly, any historical data can't be tested if you need demographics, because we're building on data, right? ChatGPT was built on data from 2021, right? And so you still can't test data that's built with historical data, right? You still can't test a model that's built with historical data, and that was why I invented surrogate classes and probabilistic fairness. So this came out of this idea of, could we use zip code to impute fairness metrics? That was our plan. We said, okay, we've got zip code, we know the demographics of the zip code, and what we want to do is make sure if you group everybody up into their zip code, we want to make sure the model's not really bad for zip codes that have a certain demographic profile, because that is evidence that the model is performing badly for people who have those demographics. And so what surrogate classes do is that it says, okay, if you know the demographic profile for that class, you can infer by changes in the fairness metric by demographic if the model performs badly for whatever demographic you're talking about. Make sense? All right. The math for this is such a good time, but I'm going to skip it. What you need technically is you need a surrogate class for every individual in your data. So every individual you're going to test for, you need a surrogate class designation, and that's that 0, 1, 2, 3, 4. And you need the full probability complement by group, right? So here I've got a not protected group and a protected group. And the idea is that the protected group is the group that we have to, that is protected by law. That's what it means. That's the parlance we use in Jurity, okay? And very key, each of these rows sums to 1. All right, so you have to have full information, and Jurity will bark at you if you don't have it. All right. So I have a pandas data frame. Works best with a pandas data frame because the indexing is really nice. I have a data frame that has surrogate class for each person, along with how the model labeled them and how the, along with how the model labeled them, that is the prediction, and how they're labeled in real life, right? So the true value and the not true value. And then I have this surrogate data frame, which is indexed by surrogate class, and it has the probability profile. And then Jurity, for every metric that you might want to calculate, and Jurity's got a pretty full complement. Jurity's been around for a while, right? So perhaps you want to calculate equal opportunity, which is the difference in the true positive rate between demographic groups. Or maybe you want to calculate statistical parity, which is the difference in the rate at which you are predicted into the positive class between groups. You have to tell Jurity, I'm interested in statistical parity. And then you just use the get score method for that particular statistic. You tell it what your prediction is, and because statistical parity only looks at the prediction rate, that's all you need to give it is the prediction, your memberships, which again is this pandas data frame that is indexed by surrogate class, and which surrogate class each of your individuals is in. Right, so I've got 2 vectors from the prediction data. I've got my labels, and I've got my surrogate class membership, and in between them I have the memberships data frame, which is indexed by surrogate class and has the probability of membership for each group. How we doing? All right. Awesome. All right. And so you run this, and you tell Jurity, this is what I want. And then Jurity is going to say, all right, it's going to run its calculation. It's actually under the hood doing a bootstrap linear regression. Believe it or not, I did a whole lot of simulations on this. Linear regression performed the best. I am open to feedback, and but so far so good, right? This is the best method we could find. And Jurity will just cheerfully print out, this is your acceptable range, and this is your statistic. And you can see the print there in the Jurity library, right? In the notebook. All right. And that's it. So if you just want to kind of use Jurity, if you've got this data, again, the hard part is the data, but if you've got, for example, everyone's zip code, and you've got the census data, you're ready, right? You're in business. Any surrogate class will work, and we'll talk a little bit about the surrogate classes at the end if we get time. All right? So again, the idea is that your model should perform equally well for everyone. You have all these surrogate groups, so you have this way to group everyone up. And if the model performs well for everyone, the model metrics should not change as the demographics in the surrogate group change. Right? And after a lot of math that covered my wall for a good 6 months, linear regression won. So what you see here is the protected group, right? And the percentage of people within that surrogate class who are in the protected group. You see a line that's mostly flat. You see a scatter plot that has basically a dot for every protected group. And on the y-axis is the prediction ratio / statistical parity. Right? And what you hope to see is that the line is mostly flat, and that statistically there's no difference in performance across zip code as the percentage of people in the protected group change. And this data was actually simulated to be fair. There's a little lift in the line, but what you'll notice is that statistical parity is actually positive for this case, which means we're actually predicting the protected group a little higher, a little more often, but not significantly often, and I know that because my inferred statistical parity is in range. Questions? Yeah. I'm going to do Scott second because Scott's my friend. Yes, sir. Yeah, the question is, does the model work? This is actually simulated data, and it's a simulated confusion matrix. So the model is beside the point, right? So the confusion matrix simulates a model that drops people into quadrants in the confusion matrix based on their demographic. And if you drop everybody in 2 locations in the confusion matrix at the same rate, then you get a thumbs up on statistical parity. There's nothing in this to test the validity of the model. The assumption is you've got a model you're happy with. And I personally, like I said, in a lot of cases, depending on what kind of model you're working on, you don't want it to be different for like women versus men or for different demographics. Yes. Yeah. Yeah, that's a good question. The question is about the statistical parity t-test. So a friend of mine, Victor Lowe, who actually helped us write this beginning of the software, is currently working on, like, do you want a t-test? What does the t-test look like? Should it be one-tailed or two-tailed? It's actually a more complicated problem than you think. Or it was a more complicated problem than I think. Right now, we're just saying, is it bigger in absolute value than -0.2? minus 0.2 is your cutoff. And I will say, if you have a very large test group, what happens to the standard error on that is that it just shoots towards 0, and then everything looks like it's statistically significant. So you've got to have some sort of, like, this is what I think is a big number. All right, Scott. Uh-huh. Yes, the question is about the formation of the data. Old school statisticians, I love it when they ask questions. So, for this to work, it is at the bottom of the notebook, but I will say this. You need a spread from 0.1 to 0.9. Like, those probabilities, those proportions need to have a spread. And so if everybody's 50-50, that's a problem. If nobody's 50-50, that is also a problem. So your surrogate class does not need to be a good predictor. In fact, this works much better if it isn't. If your probabilities are evenly scattered. If there are cases where you're actually really bad at telling who's who, because the fit of that line depends on having a mean to go through. So, so absolutely, this probably would not work for male-female. Because everybody sits right at 0.5. It works nicely for a lot of other demographics. Yeah, nice. All right, yes. Yeah, no, I love that question. So the question is actually about the fit of that line. And what I was taught way back in grad school was omitted variable bias. So if you have something that's correlated, it has to be correlated with the demographics of the zip code and correlated with your model performance. It has to be correlated with both of those things. It can create a bias in this calculation. That can happen. What I have, as we've tested this in various situations, in fact, I'll go ahead and scroll down to the Home Mortgage Disclosure Act. So we actually built a model on mortgage granting, and that data includes demographics. And we tested it. We tested it for bias, white versus non-white. I'm also checking the time because I promised not to go over. So what surprised us, I thought exactly what you thought, that this is going to totally mess up our calculations, and anytime we try to do anything real, it's going to punk us. But the numbers are surprisingly good. So if you look at that, we're off by, I consider that a rounding error. Look at the absolute difference in the numbers. And so that made me really confident on pushing this out. It would have been a little research project if we had not been able to show that it worked on real data. That doesn't mean it's going to work every time. And that is a caution for using this software. This is inferred. It's a statistical model. On your surrogate class, so let's get down to all the way down. I had so many things. This is going to be in my GitHub repo, so don't feel like you're missing anything. All right. Let's see. What else do I need to know? Calculation stability depends on the inputs. So protected class probabilities have to have a range. You need at least 100 surrogate classes. It works better the more surrogate classes you have because you get a more stable fit. And you should have 20 to 30 individuals per surrogate class because that makes the probabilities stable and it makes them converge to a mean or converge to a normal with the right mean. If you don't have those things, particularly if your inputs are really skewed, you can get really crazy answers. And one of the things I do recommend is drawing this plot, right? Draw that plot for yourself. Yes? Yeah, so that's a good question. This is about quality of inputs. It's like everybody took my statistics classes as an undergrad. So that is called measurement error. Measurement error, so the question is demographic shift, and if you use the census from 2020 and 2025, you're gonna have a very different answer. So thing number one is that they do actually update the census numbers. So you've got the official full count, but they do interim counts. And they're not, they're done differently. They're done with like a statistical sample, but yes, absolutely use the data that is as close to your time period as you can. The other thing to keep in mind though, there's a lot of talk about undercounting in the census, and that is something that keeps me up at night because that will create measurement error. Measurement error will bias your statistics towards zero, and this number biased towards zero means you're saying it's not a problem when it is. However, again, I thought that was going to be part of what tanked these numbers, and it didn't, and I don't know why. This is something that you get comfortable with when you do research. You look at a number and you're like, I don't know what happened, right? But the absolute value for the inferred metric is actually larger than the oracle value. And so again, I thought measurement error was going to be a big problem. It doesn't appear to be as big as I thought. Yes? Yeah, the question is about small probabilities, small counts, and whether the software accounts for that. Generally it does. It's pretty robust to that. Logistic regression is the reason it works so well on this is because it's really the simplest possible method, which makes it really robust to data problems. The caveat there, again, is the same caveat I said before. If everybody, like if all of your probabilities, for example, for your dominant class are stacked up around 1, and all of your probabilities for the smaller class are stacked up around 0, the line's not going to be very stable. You're going to have a hard time fitting it. But it does know that the proportions are smaller. Yeah. Yeah, okay, wait one sec. Okay, we are at 11:13. I'm going to make that my last question. Again, this is all in my GitHub. I am MF Thielb. I am the only Melinda Thielbar on the internet. So if you look for me, you will find me Thielbar. We welcome contributions. We welcome feedback. Feedback is a gift. This stuff is too important for us to screw around with it. You find a problem, tell me. I can't promise I'll fix it right away, but I also will not just blow you off and say, all of my math is perfect, you guys are silly. Thank you so much for your time. Thank you for the questions.